Good morning, good afternoon, everybody, and welcome again to this second session of the Ozone CCI workshop. And before starting the workshop, I would like first to thank you again, Jean-Christopher and Victoria, for managing the good discussions yesterday, and also to thank all of you who contributed for these good discussions. And just to let you know that we took good notes of all the points raised and all the suggestions and recommendations, and this will be taken up for sure. So, like I mentioned yesterday, the feedback that you provide is very important for us, and especially we intend to take this into account when planning the evolution of our activities together with ESA. Okay, so today we decided to give the floor to users and to listen to them, and we look forward to learn about science applications. So we leave a bit away the data for today, and we look a bit more about what can be done with these data and interesting science applications. So like yesterday, same format, 20 minutes of time slot for each presentation, 15-minute talk and 5-minute questions. Try to keep to the time slots because we don't have too much time to extend the overall sessions. And again, as yesterday, use the chat to enter your questions, and we will manage this during the questions. So that's all for the introduction. And unless Martin would like to say something, I would prefer maybe to give the floor to Melanie and Catherine, who will share the first session.
Yeah, I agree.
You want
to hand over to the chairs.
Very good.
Okay, hello everyone, and in the first session of today, which is dedicated to the science highlights and international initiatives, we will hear 5 presentations, and the first speaker will be Birgit Hassler. Birgit, please.
All right, let me share the screen. We tried that before, so hopefully everything goes smoothly. All right, can you see it?
Looks
no.
good.
Looks good. Yes, we do.
Okay. All right, perfect. Well, hi everybody. I was invited by Martin Dameris to talk a little bit about the 2022 ozone assessment, and in more general also about how the ESA CCI or long-term data sets can be used in international assessments. So I have come up with 3 different questions where I think I can talk about what I think I can talk about in that presentation. So the first one would be, what are the requirements of data sets to be used in international assessments? The second, then in more detail, where have ESA ozone data been used in international assessments? And I will indeed talk a little about the chapter structure and timeline of the WMO ozone assessment that's coming up. So I will focus for the international assessments mostly on the ozone assessment, but also a little bit on Lotus and TOAR. So for me, the interesting questions for dataset characteristics were focused on trend analysis, because that's one of the main things that we report upon in the ozone assessment. And so I think it was worth just to reiterate what kind of data set you would want to look into trend analysis to make sure that that you can have a good analysis and reliable results. So for trend analysis, we would like to have long-term measurements, preferably if it would be a single instrument, but if that is not possible, then of course merged data sets are fine as well. The data sets, the measurements should be stable and processed in a consistent manner so that you have a good grasp on the bias and drifts that should be well validated. And we have seen plenty of validation efforts and validation studies yesterday. We would want the data sets to be well characterized in the uncertainties. And one thing that is probably not very data set specific, but would help tremendously for the usability of the different data sets is that it is well documented in the peer-reviewed literature, so that it is basic, the community knows about it and it's advertised, so that the community knows what the data set can be used for, like what kind of studies are possible with the data set and where to get the data set. So, and we have seen already yesterday that some of the ESA CCI ozone data sets fulfill these requirements, and those are probably not the only requirements that you want for data set characteristics for trend analysis, but I think those are some of the main features that you want to fulfill. So what we did, and where we started, or we didn't really start there, but one of the main activities that had happened in the last years is the Lotus activity. This is a Spark activity that started in 2016 and is in the second phase right now. It looks at long-term ozone trends and uncertainties in the stratosphere, and is one of the main studies that have been, where like the merged data set have been compared in a consistent way. The Lotus activity is following up the SI2N activity that evaluated ozone profile trends from long-term satellite and ground-based records. In the phase 1, Lotus focused mainly on global ozone trends. In phase 2, the focus shifted a little bit more to also regional trends and comparisons between stratospheric and total column ozone trends. So on the right, you see the cover of the report from that activity that has been, it's a Spark report that has been published in 2019 and is publicly available. And there's all kinds of analysis in there, and about different trends and different data sets, and also kind of the stability of the different data sets and the trends that we get from the different data sets. And I just want to show one of the results that came out of that report. What you see here is the ozone profile trends for different regions, different latitude bands, and for the pre-1997 trend, the declining trend basically, and the post-2000 trend, that is the recovery trend. What I want to point out here is not really the different, like the magnitude of the trends. Wolfgang will talk about that in a bit and in all detail. What I wanted to point out is that the different colored lines show different ozone data sets that have been used for that comparison. And one of those ozone data sets is an ESA CCI or an ESA data set, the SAGE CCI OMS that was described yesterday as well as a data set, and it has been used extensively in the Lotus activity and consequently also in the ozone assessment, because what happened, a lot of the analysis and results that have come out of the Lotus report have been used in the ozone assessment in 2018. For the ozone assessment, several chapters need long-term data sets for important analysis. It's dependent on that. For example, the chapter 3 of global ozone, or chapter 4, the polar ozone chapter. What goes into the ozone assessment is often based on activities like Lotus, because it is really the community comes together and it's a nice, concise way of looking at things and compare things. But also the assessment relies on individual studies and figures from peer-reviewed literature, where data sets have been used, merged data sets or other data sets. And that is one of the things where people can make sure, or can advertise what they have found for the ozone assessment, for example. In the following, I will show a few examples from the ozone assessment studies or figures that have been published in the last ozone assessment, and that contain ESA CCI data, ozone data. One of the examples here is the ozone anomalies in different on different pressure levels. Here you can see on the left the ozone anomalies at 2 hectopascal, and on the right at 10 hectopascal for different latitude bands or different regions. And you can see all different kinds of satellite dataset, merge datasets, including again SAGE CCI OMS dataset that was included in the Lotus report and therefore consequently also got into the ozone assessment. So that is an example from chapter 3 that was led by Peter Brasica and Jessica New. Another example is, for example, here the post-2000 trends, so the ozone recovery trends. Again, it's one of the examples that where different merge data sets, including an ozone ESA CCI data set, have been analyzed for trends. So this is in as a function of altitude or pressure and different latitudes. That figure has been shown yesterday as well, but it's one of the prominent figures of like how the data, the merge data, including the ESA data, is prominently represented in the ozone assessment. But it's not just the vertically resolved ozone that is of importance for the ozone assessment. Total column ozone is also equally important, and that is one of the examples, again, from chapter 3, where also ESA ozone data has been represented in that study. And it's an adaptation from a paper that Mark Weber published in 2018 and shows the total column ozone evolution for different latitude bands. Again, that is chapter 3, but it's also the next example is an example for chapter 4 that has been led by Ulrike Langematz and Matt Tully, where you can see an analysis of GOM2 and Skiamaki total ozone data, where it shows the spring to autumn ratio of observed high latitude total ozone versus the 100 hectopascal winter eddy heat flux. And it's based on ESA data, and it is an update of, again, a study from Mark Weber from 2011, but it is a really nice example for what the data can be used for, and that you have a study that is not part of an initiative like Lotus, for example, that is prominently represented in the ozone assessment. Besides the stratosphere, there's also the troposphere that is of interest in the ozone assessment, and this is an example again from chapter 3. It shows a time series of tropospheric ozone columns for different satellite records. There's also many of the ESA ozone data included in here, and it is a really nice example for how studies from the tropospheric ozone assessment report found their way into the ozone assessment. So Jessica New will talk a little more about the TOAR phase 2 in a bit, but this is an example from TOAR phase 1, which I will explain in a little bit, but this is from a paper by Audrey Goodell in 2018. So the Tropospheric Assessment Report 1 was a science effort initiated by IGAC, and it wanted to make sure that there is an up-to-date scientific assessment of tropospheric ozone's global distribution and trends from the surface to the tropopause. They wanted to make sure that there is a literature available with new analysis, and the data that is used for that analysis is easily accessible and documented. In phase 1, it was not the report was not one document, as for example the ozone assessment, WM ozone assessment always is. It consisted of 8 publications. One of them was Audrey's paper, where I showed the graph from that got into the ozone assessment 2018. It's 8 different publications that were in a special issue in Elementa, and And the phase 1 also included a web accessible database of ozone observations. And I think that is one of the really important things that people can see with the publications, what you could use the data for and get ideas, and then the data is readily available. And so some of the ESA data is in that database and therefore very prominently placed for further studies in the community. The TOAR report did not, like, there was not just that one figure coming out of the TOAR report. So one of the other analysis that is represented in Audrey's paper is shown here, and it's just another example where the ESA data, ESA also data has been analyzed. It shows for 1 month, August 2009, partial columns for ozone from the YASI and GOM2 product, and you can see on the left the partial column for the lowermost troposphere from the surface to 3 kilometers, and on the right the mid-troposphere 3 to 9 kilometers. And so it's a very nice example of what the data can be used for. To get finally to the ozone assessment 2022, there is not much to say yet besides like the chapter outlines and the timeline, because we just started with starting to look into how to structure the different chapters. I am part of the lead team for chapter 3, the global stratospheric ozone chapter, together with Paul Young from the University of Lancaster. As you can see here, there's 6 chapters that are relatively common or have been in the ozone assessment before. That would be the ozone depleting substance chapter about HFCs, then the global stratospheric ozone and the polar stratospheric ozone chapters, the stratospheric ozone changes in climate chapter, and the scenarios and information for policymakers chapter. A new chapter this time round would be the chapter 6, where it deals with stratospheric aerosol injections and impacts on the stratosphere. And if you want to know a little more about that, I think Paul will be happy to tell you why exactly there is a new chapter, why this is prominently placed. Yeah, so I just wanted to point it out. There is a new chapter in there for the 2022 assessment. The timeline for the ozone assessment is as follows: that we have to submit an extended chapter outline until the mid of April. In July, at the end of July 21, we have to submit the first order drafts, and then the second order drafts in January 22, after we have done the review for the first order draft, of course. And then in April 2022, there is the final draft due, and the final submission would then be the end of the year 22. I wanted to point out one thing that is not on the official timeline, but I wanted to point it out anyway for the community. That is, if you want to, if you have a good idea that you think is important for the assessment, and you had like a paper planned, then I just wanted to point out that in May 22, there is the deadline for the papers to be accepted so that we can cite them in the assessment. So or around May 22, it's not entirely clear yet, but around that time. So if you have a good idea, or if you have planned on writing something about like with the ESA CCI ozone data or some kind of really cool study, then please go ahead, do so. Keep that deadline in mind. So yeah, to sum up, the long-term data sets of high quality and well-defined uncertainties are essential for reliable trend analysis, as they are used in international assessment reports. The satellite measurements from the 1980s and 1990s are becoming less important for the trend analysis, with more years of measurements available during the 2000s and 2020s. So shorter satellite records are not like just kind of like selected out because they just start sometime in the 2000s. I think the declining trend is not that important for the trend analysis anymore, not necessarily. Then the satellite and the ground-based measurements are very important for the model evaluation and validation, for example, for specific regions or case studies, even on shorter timescales. And I have been talking a lot about the merged data sets that you have been seeing, that have been represented in the different in the different assessments. I think the individual data sets are also of equal importance. If you have a nice study that uses that data, then these data sets can also be represented in any of the assessments. If there is a publication about it and it shows cool results. Okay, that was my presentation. Thank you.
Okay, thank you, Birgit. I can see 2 questions in the chat. Jos, can you please? Okay, I see they have been already answered by Paul. Are there more questions for Birgit? Okay, if this is not the case, we can move on to the next speaker, which is Wolfgang Steinbrecht.
Yeah, thanks for giving me the opportunity. Thanks, Birgit. Can you see my slides?
Yes, it's fine.
Perfect.
Okay. I'm starting with a slide that I've used before. I'm going to talk about trends in total column ozone and in stratospheric ozone. I'm the speaker, but there's a lot of people that kind of on a regular basis contribute to what I'm talking about. Mark Weber is always leading the BAMS State of the Climate, where all the other people that are named here usually contribute last year's data. So we have a very good group there that updates things regularly, and some of the people obviously are Ozone CCI people as well. Now, why have I picked this introductory picture? That's because it's taken from my office, and I've been working on the stratosphere for about 30 years now, but it's very rare that I can see the stratosphere. But there you see this mother of pearl cloud, and we think that was an alpine stratospheric cloud. Now, to get stratospheric clouds, you need cold temperatures. So I thought I'd start with temperature. This is from chemistry climate model simulations, goes from 1960 to 2050, so almost 100 years. And it shows that the chemistry climate models are saying the stratosphere should be cooling by about 8 Kelvin in 100 years, which is a lot more than the 1.5 Kelvin we want to keep in the troposphere. And the main culprit is CO2, which I've plotted in magenta here. That's the Mauna Loa time series with a scale on the right. And what you can see is as the CO2 is going up, the temperature is going down. And you can even see from the 80s to the mid-1990s that the declining ozone had something to do with that as well. Why does CO2 cool the stratosphere when it increases? Well, it keeps more radiation in the troposphere, so less infrared radiation is going up to heat the stratosphere, and also more CO2 in the stratosphere is great for radiating to space, so that will also make the stratosphere colder. Now, models are one thing, data are always better. So I showed time series here from rockets, from satellites, which start sort of in the late 70s. And being a ground-based sky, I've also thrown in 4 NDAC LiDARs. And it's actually surprising how good a job the 4 NDAC LiDARs, all of which are in the Northern Hemisphere, do showing something that's near global. There's also NCEP analysis in there, and one of the things you can see in the data, of course, is the 11-year solar cycle. Now, that's another thing I wanted to say. If you look at a 10-year time series like Envisat-MIPAS, that's great data. That's CCI data, actually, but it only tells you part of the whole story. So we need these long time series as well. Now, really, I'm supposed to talk about ozone. So here's the same kind of plot for the upper stratosphere, 60 south to 60 north for ozone. And the gray is what the models say. And the pink or the magenta is the chlorine, again, on an inverted scale. So as the chlorine goes up, the ozone goes down. And if you look, one of the interesting things about the chlorine change is that the increase in chlorine, or the downward slope in the 70s, was about 3 times larger than the recovery slope. So the recovery will basically take about 3 times as long. Now, if you look at the chlorine line, it doesn't go up as much after 2000 as the ozone line does. And why is that? Well, that's because of the cooling. And what the cooling does, it slows the gas phase normal chemistry in the upper stratosphere, and it helps to bring the ozone up. So we have kind of this super recovery in the upper stratosphere, and some of that also in the lower stratosphere, where ozone is going up or expected to go up faster than just from chlorine. So this already tells you that there is a link with CO2 changes and climate change. Again, let's put some data in there. You notice that some of these time series, or all of them, pretty much go to 2020. So Birgit already showed many of these. That's the SPUV data extended with the nadir arms. Then there's Gauss cards and swoosh in there, which is largely MLS in the last couple of years. There is a lighter blue one, which is SAGE CCI OMPS LIMB, and then there is another version of that if you want from the Canadians, which is SAGE OSIRIS and OMPS LIMB. I again have put some ground-based data in Umkehr stations, which are sort of the records that go back the furthest in the past, and the 5 NDAC LiDARs again. The Umkehr and the LiDAR show larger changes, and some of that is because they're at higher latitudes, whereas the satellites are near global, and things are changing a little bit less at lower latitudes. Now, we all know there was this large decline, largely due to chlorine, and one of the big questions, of course, now is ozone going up as we expected? And if you just sort of hand plot here the line, it looks like there is a recovery. I've taken the LiDARs, which make the recovery larger. If you take the satellite data, the more global ones, it'll be less big. And so one of the questions always is, when we look at these trends or these slopes, are they significantly different from zero? Are they going up or going down? The standard technique is multiple linear regression, but there's also other techniques like dynamic linear models. All of them probably have in common that you have to account for some of the variability, and then you can have large fights about how many regressors you put into these things, but overall it doesn't matter too much, and if you do more or less the right thing, the results are more or less the same most of the time. Okay, so that was looking at near global. Let's look at the latitude altitude cross section, and again I'm looking at model simulations, and one of the nice things with the models, of course, is you can separate things out. In reality, you always get thrown everything at you. So the models can separate things out, and here we're looking at the ODS effect of the recovery. It goes from 2000 to 2100. And what you can see basically is 2 regions, the upper stratosphere, which is about 40 kilometers, which is the region we just looked at, and the model is saying ozone should be going up by about 20%, 10 to 20% in the next 100 years. And it's more or less consistent with what we observe. And the other region where you see the large changes is the Antarctic ozone hole, which is supposed to pretty much disappear until 2100. Then there's a region around 30 north to 60 north and lower stratosphere, which is important for where we live and is also important for total ozone. That's supposed to go up as well. But I'm going to warn you about that region. That's a very messy region, lower stratosphere, lots of variability, lots of layers, lots of things going on. So I'm going to talk about that a little bit more. So this was looking at the recovery effect from the ozone depleting substances disappearing. The 2 regions where we really see significant recovery is upper stratosphere, or beginning recovery is upper stratosphere and Antarctica. And this is looking at the climate change or CO2 change effect of the same thing. And you can see, again, at 40 kilometers increases. So that's what I showed you in one of the earlier slides. The stratospheric cooling up there helps to bring the ozone up. And again, it's about 10 to 20%. So it's comparable magnitude as the ODS recovery. The second big region you see here is the lower stratosphere in the tropics or in the subtropics, where the models predict an increase of the Brewer-Dobson circulation. So you're pushing air up higher and faster, and you bring up ozone-poor air, and that leads to large ozone decline in the lowermost stratosphere in the tropics. And this here is the messy region where you have a lot of variability. You can already see that in that plot. You have increases and underlying decreases. Everything is hatched out because it's not significant. So that's an interesting region or a complicated region, depending on how you want to look at it. So this slide tells us that climate change, but also dynamics, are very important for the future of the ozone layer as well. This is the same slide I just showed you, and on the right I have a plot from the new paper from Will Ball from ACP 2019, which shows the observed trends from 1998 to 2018, and this is largely based on Gauss cards. And again, you see the increase in the upper stratosphere, some of which is, of course, coming from the ozone, from the decrease in the ozone-depleting substances. You see the large decreases in the lowermost tropical stratosphere. And then here you see this region where what Will sees does not agree with what the model says. The model says it should go up there, and Will sees decline here. But as I said, this is a region of large variability. So the thinking now is that we're probably seeing decadal variations which may go away. It's a little bit like the climate and weather thing. We know that climate is warming, but actually at Hohen Peißenberg today we got 20 centimeters of snow, and 2 weeks ago we had plus 20 degrees. So it's more the variability here that you see and not the long-term climate cycle maybe. And this just shows the ozone depleting substance effect again, so I'm just going to go over that. Okay, this was just one set of trend data, and Birgit has showed slides like that. This is from the well, this is trends processed my way, same as in WMO 2014, shows latitude, altitude cross sections. On the right, you have SPUV, on the top the NASA, on the bottom the NOAA, extended with OMPS. In the middle you have the CCI data sets. Top is the CCI SAGE, CCI OMPS LIM. Bottom is with OSIRIS, and the two on the left are Gauss cards and Swoosh, which are largely based on MLS. And these trends here go to 2016. These are the things where we see some significant increases. Now in this analysis, the Antarctic is not significant yet. One of the things to keep in mind is the large averaging kernels of the SPUV data, which smear things out a little bit and can shift things in altitude and don't give you too much information in the lower stratosphere. This is the same thing, but now to 2020. And if I go forth and back between these two, you basically can see that there is not a whole lot of change with 4 more years of data. So we get a consistent pattern and magnitude. We have a number of data sets, which is important, and we have 3 instrument types. And I haven't even talked about the ground-based data, but they pretty much confirm this where we have them. This is again put in the slide from Will Ball's paper, where you can see some differences in the lower stratosphere. So this may come from the analysis, and maybe Will's is better than the one that I've been doing here. And you can see similarities and some differences in this controversial, largely dynamically variable region here in the lowermost stratosphere in the northern extratropics. So some of these details are not resolved. Decadal variability plays a role. There may be slight difference between instruments and things. Altitude resolution is certainly an important thing. And we do have a spark activity that really looks at this region. And we'll try to get a much better handle on that than that spark octave. So there will be a talk about that later today. So it'll be interesting what Irina tells us about that. Or is it Peter Hoare that's giving the talk? This one I'm going to skip. It has a lot of lines, and the bottom of this is that there is no big changes from WMO 2014 to 18 to when you go with data to 2020. So that's probably a good thing. Okay, so far everything was about profiles. Let's go to total ozone, and I have to thank Mark Weber for these slides that I just got yesterday, I think. This is looking at 60 south to 60 north. You see the decline with 1.5%. And if you start in 1979, I think, no, in 1997, you get some kind of significant increase. It's roughly this 3-to-1 ratio that you see. But if you start, for example, in 2000 or 1998, then that kind of goes away. So for total ozone near global, we don't really see a significant increase yet, but we are in this wide band of CCMI models. So there's nothing happening where we're saying, well, we should really be worried about anything. And this just says that again. Now this is looking at the latitude pattern of the trends, and on the bottom in blue you see the declining phase from 1979 to 1996, and on the top you see the increasing phase from 1997 to 2016, and it goes from -60 southern latitudes to 60 north. Now, if you think of this 1 to 3 rule of thumb, and somebody's probably going to call me out or call me stupid on being that simplistic, but I think it's a nice thing to look at. So we put this in here, we divide it by 3 and we flip it, and this is what we would expect for the recovery. And what you can see is there's not much recovery expected up to about 30 south or 30 north. As you go higher, we maybe can hope to see something. I think the error bars are 2 sigma, but Mark can answer that question. So it looks like at higher altitudes, ozone is not going up as much as expected. And this is looking at 1997 to 2016 data. This is the same plot going to 2020, and I'm going to put the same thing again in there. So in the southern hemisphere, it looks a little better. In the northern hemisphere, it looks worse, like the recovery has kind of completely disappeared. But then Mark has also done a regression where he adds to the things that are shown at the bottom, ILT, QBO, solar, volcanic, and so if you add dynamical proxies, the Arctic or Antarctic oscillation, and the eddy heat fluxes, then you get this picture. And if you do the 3-to-1 on that, you almost get a perfect match. So that kind of tells us that from the ODS side of things, total ozone is evolving more or less as we expect within these error bars, which are significant. Consider it the small trends that we have, which are only like 1% per decade or less. So the dynamics is important, and when we put it in, we get better consistency with what we expect from the ODS. This is featuring some of the nice things we can do with the new data sets. Monika Selak, which is a CCI person, I think, or a CCI data set, has looked at seasonal trends, and you can see larger trends in the winter, which is kind of what you would expect, that when it's colder, you see more of an effect in the upper stratosphere. Victoria put out this Megridop data set, which is also a CCI data set, which is the total where you can make maps, and you can see higher trends over the North Atlantic. I think that was shown yesterday. And there's a similar paper by Carlo Arosio, which shows the same thing. So there's new things we can do thanks to CCI and thanks to the time series getting longer and the data sets getting better. So we can do more detailed things, but I would argue that not everything we see there we understand. Dynamics probably plays a role, and there's a lot of things that can be done there. That brings me to my summary. I think that the trends that we've seen after 2000 are pretty much consistent with expectation, and we see the clearest signs of a recovery where we saw the largest ozone depletion, which is the upper stratosphere and Antarctica in spring. One thing I can't stress enough is that this recovery is a lot slower than what we've had with the pre-1997 decline. So when it took 15 years or 20 years to see significant declines, we can expect that it'll take a lot longer before we see significant increases. And that also means that as we go from assessment to assessment, things aren't changing too drastically. We can't really expect that. Climate change and dynamics are very important. I think I've shown a number of slides on that. For example, in the lower stratosphere, it's important. And one of the things that's very important, I think, and that's at the bottom here, is that we absolutely need multiple and independent measurements. And as we all converge more on using the same data and the same methods, we have to be a little bit careful about having independent and reliable data. 1% per decade still remains challenging, and being a ground-based guy, of course, I say space is great and it gives us a great picture, but ground-based has the long-term and only the single stations, but also you can fix an instrument easier, and overall it's a little bit cheaper, at least for one station. So thanks very much. That's what I wanted to say, and I'll go back to my Alpine stratospheric cloud.
Okay, thank you, Wolfgang. There's one question. Björn Martin is asking if there are any publications on ASCs.
Yeah, there's a little bit. Nobody really observed that thing. I think they saw it the most in the Val d'Aosta, where they detected, I think, with a LiDAR aerosol at the high altitudes. But this is above the Zugspitze, and unless the Innsbruck guys got something, we didn't have a measurement there. We just saw it by eye.
Okay, and Sophie, can you ask your question, or is it a comment?
Yes, hello, Wolfgang.
Hi.
Yes, when you showed the plot decreasing trend up to 1995 and said that then you have a better agreement with this ratio of 1 to 3, I was thinking that the decreasing trends were contaminated by Pinatubo aerosol.
Yeah. I agree, and you can see in the total ozone by Mark that things change when you don't start in 1996 or 97. So for many things, I like starting in 2000 when Pinatubo is over. But the regression to some degree should account for Pinatubo.
Yes, I can only agree. The Pinatubo aerosols are in, but they're not always perfectly matched. So I think there is some not a perfect match. And also, I think that's why, for instance, piecewise linear trends are much more problematic, because that ejection point always moves a lot of down, and it also strongly depends on the aerosol effect.
So what I wanted to add is that finally trying to get that 1 to 3 ratio right really depends on the year you are taking into account in your regression.
Sure. It also depends on the ESC you're using, because they have other slopes too. So it's sort of a sanity check more than a really strict check.
Okay, there's one more question from Irina.
Wolfgang, really great presentation. Love it. You
Thanks.
always do great presentations. Very clear. So when you were discussing the total ozone trends that you guys published in the BOMs, and mentioned that the importance of dynamical proxies, for getting things well, right. I don't know what right means, but that changes the trends in total ozone. Should we really pay more attention to the dynamical proxies when we're doing analysis of the ozone profiles? And would that be an issue when we compare total ozone versus stratospheric ozone versus tropospheric ozone? Would they help? I mean, to include the dynamical proxies?
Oh, that's a big question. In this case, it looks like they help. But Paul, I remember having discussion with Paul years ago, and Paul said, "Oh, you shouldn't have any proxies in there." So the more proxies you put in, the more you kind of put the answer into things already. And there is correlations of some of these dynamical proxies with ozone changes, and basically one of the things they often do is the proxy picks up short-term variability and translates it into trends in long-term variability, but the mechanism that are acting on the longer timescales may not be the same. So they're probably not the ultimate answer either, but there's certainly something that gives you another perspective on the same thing. And they tell you that some of the changes, well, we know some of the changes are dynamically. Whether we can take them out well is a different question. But in this case,
Yeah,
it works very nicely.
Just to weigh in on my comment there, Wolfgang, proxies have to use with, I think, a lot of thoughtfulness. That is, for example, the heat flux is a proxy for the W star, and W star is latitudinally resolved. You can do it pretty well for the polar regions. For the mid latitudes where W star actually changes sign, it's not well done. Also, the trends in the heat flux in W star are probably different, so their impacts in different years on ozone advection depends on ozone itself. So proxies have to be really well thought out in how they're used. So I'm not arguing against proxies, but I would say that one has to have an explanation of why you're using it and how it's actually applicable.
Yeah, now we could probably put, I don't know, traffic numbers in the US in there, and it would correlate with something and take something out, but it probably doesn't change ozone.
Okay, I think we should move on. The next presentation is given by Jessica New. Jessica?
There's a bunch of background noise here, so I'm going to put on my headphones. Just started. Let's see. I apologize. Can you hear me okay?
Yes, fine.
Oh. Can you hear me?
Yes, we can hear you.
Yes, perfect.
I think I can't hear you, so let's try it this way. Okay, so I'm just going to give an introduction to the tropospheric ozone assessment report and then talk about plans for satellite ozone intercomparison as part of the report that will be done by the Satellite Ozone Working Group, which Paul Palmer and I are leading, and Helen Worden is our steering committee member. So this is the TOAR steering committee. TOAR is basically led by Owen Cooper and Martin Schultz, and then we have wide international representation on the steering committee. So Birgit already gave kind of an introduction to the first tropospheric ozone assessment report. So there, the purpose was really to provide the research community with an up-to-date assessment of the global distribution and trends in tropospheric ozone. And so we delivered this report that was made up of individual manuscripts, as Birgit pointed out, and also created this database of ozone exposure metrics that were relevant to human health and vegetation, as well as an assessment of satellite ozone and ground-based ozone that is relevant to climate. So these are some of the TOAR-I publications. They were all published in Elementa, and so the one that we're mostly going to be talking about here is this one called Present Day Distribution and Trends of Tropospheric Ozone Relevant to Climate and Global Atmospheric Chemistry Model Evaluation. So TOAR-II is a little bit different than TOAR-I. The final product for TOAR-II is an observation-based up-to-date assessment of tropospheric ozone's distribution and trends. But the difference here is that the first sort of stage of it is to assess the physical science basis for ozone's global distribution and trends. But then there's also a focus on quantifying the impacts of tropospheric ozone on human health, crop and ecosystem productivity, and climate change. And one important point is that studies can be policy relevant, but shouldn't be policy prescriptive under TOAR-II. So TOAR-II is going to be kind of split into two stages. The first is to generate a set of papers that will be contributed to the TOAR-II community special issue. So those papers are developed through the focus working groups, such as the Satellite Ozone Working Group. The papers contribute to the TOAR-II objectives and support the final TOAR-II assessment and make use of the data resources that are collected as part of TOAR-II. And then the second set is, or the second stage is an invited set of core papers that comprise the actual assessment report. Those will then be developed by to be determined assessment working groups. At present, the only specified core papers are updates to TOAR Health, TOAR Climate, and TOAR Vegetation, and then additional core papers will be identified by the steering committee based on input. So here's an overview of the status and sort of a roadmap. So in 2020 was when the new steering committee was selected and the planning of objectives. And 2021, we just had our first TOAR-II kickoff workshop. We're forming the working groups and beginning new data collection. In 2022, that's when the planning for manuscripts and initial data analysis should be completed. And then we'll be developing new ozone metrics and populating the TOAR-II database. 2023 is finalization of the database and completing data analysis. And then the submission deadline for the community special issue is September 1st, 2023. And then 2024 is when the actual assessment will be published. So Birgit talked a little bit about the TOAR-I satellite ozone intercomparison. Again, this appeared in the Godel et al. Paper in 2017, and it really represents sort of a first attempt to intercompare tropospheric ozone records from multiple satellite instruments. So this table shows the various products that were included. So there was the OMI MLS tropospheric column. There was a GOM and OMI merged record from SAO. There's an OMI record from Rutherford Appleton Laboratories, Iazi-Forley and Iazi-Sofrid, Skiamaki, and TESS. Although TESS doesn't have as long of a data record, so it wasn't included in some of the trend analysis. So this is showing the distribution of tropospheric column ozone, or TCO, from 2010 to 2014. And up in the upper left is the Dave Tarasik's TOAST product. So these are trajectory mapped ozone sondes. So you can see that even in terms of the basic distribution of ozone, there are similar features, but there are differences in, for example, the latitudinal gradients and in the magnitude and strength of some of those features that are fairly significant. And then when we go to look at trends in the tropospheric ozone burden, so the top left panel is for 60 south to 60 north, and then we've broken it down into 0 to 60 north in the middle and 0 to 60 south on the bottom. And so you can see that there are these very large differences in the trends in tropospheric ozone burden. The Iazi records both indicate a decrease in tropospheric ozone burden. The other records mostly indicate an increase, although Skiamaki is much less of an increase. And there are huge differences in the variability of the tropospheric ozone burden. And so this is really what spurred us to take a closer look at these records in TOAR-II. And over on the right, I have the NOx emissions from the tropospheric chemistry reanalysis from Kazu Miyazaki. And so these are the changes in NOx emissions from 2005 through 2016. And so you can see it's not easy to set an expectation for what tropospheric ozone should have done over this period. because there have been very large changes in the emissions with increases and decreases and turnover within the time period, etc. So, so knowing what to expect is not even straightforward. In addition to these sort of global pictures, we also looked at regional trends in tropospheric column ozone. Again, you can see huge differences here. The TOAS product is again this trajectory mapped ozone sondes. OMI-MLS shows positive trends basically everywhere, whereas the SAO and Rutherford records are more of a mixed picture. And then EASI, the EASI products again show declines in tropospheric ozone from 2008 to 2016. So some of the so Paul, yeah, that's what TOAR-II is all about, is narrowing the uncertainties on those trends. So some of the possible sources of trend differences that were identified in TOAR-I are number one, changes in stability or retrieval quality with time, or changes in sampling with time. If we look at the Boynard et al. Paper from 2016 on the EASI Forley product versus ozone sondes, the conclusion of that paper is that there is no significant change in the relationship or in the bias against ozone sondes. And that is true, but if you look closely, you can certainly see that in around 2011 or 2012, there is a more negative deviation from the ozone sondes than there is in the earlier period. And so while it's not statistically significant, it's clear that there is a decrease in the tropospheric column, the surface to 300 hectopascal part of the column, even though there's remarkable stability of the total ozone column. So we don't see the same thing in the total ozone column. Some of the other products include drift corrections, and so that's always a question of, whether that has been applied properly. And then there's obviously big differences in vertical sensitivity of these different products. So on the bottom, you see the averaging kernels for the different products. And so they're all sensitive to different parts of the atmosphere. And so therefore, the atmosphere itself may have different trends at different vertical levels. So, so Paul and I put together the Satellite Ozone Working Group for TOAR-II with the goal of trying to understand that this wide variety of trends and variations in tropospheric ozone that was reported in TOAR-I, and provide an improved and updated estimate of the trends. And so, so we're taking a couple of different approaches to this. So the first is that we want to make sure that all of the products that go into TOAR-II are evaluated not just for their bias against ozone sondes, but for how that bias changes with time. And so the idea here is to calculate monthly mean bias of the partial column ozone from each instrument relative to ozone sondes for probably 5 to 6 latitude bands for the entire length of each satellite record. And here's an example on the left of where we did that for TESS. So this is 464 hectopascals northern mid latitudes. So this is the difference between TESS and ozone sondes as a function of time. And you can see that TESS was actually remarkably stable over that time period. And then, the Boynard et al. Paper was a similar attempt with EASI, and actually does indicate that there are some changes in the consistency of the product with the ozone sondes with time. So so here we're going to specify a format for the satellite ozone records. And if the instrument groups are able to provide the data to us in that format, we can assess the bias against the sondes. If not, we can provide this methodology to the instrument group and ask them to do the sonde comparison. So we're working on sort of writing up that methodology. And then the second approach is to look at how much the differences in the trends are driven by differences in sampling patterns and vertical sensitivity. And so here we are going to use a chemistry transport model. We will likely use the tropospheric chemistry reanalysis run without any assimilation of ozone records, but with assimilation of ozone precursors to generate these 40 ozone fields. And then we will use the sampling patterns and vertical sensitivity of each contributing satellite instrument. And there's a couple of different things that we can do here. One is to see what the differences in the simulated measured trend are relative to the actual trend from the model for each of the instruments. And the other is to use a single year of the reanalysis repeating over the entire record of each satellite instrument, and then sample it with the sampling pattern and averaging kernels as they changed with time to see whether any of the instruments actually introduce a spurious trend to quote unquote data that shouldn't have a trend. And so that's the second approach here, to try to understand what it is that drives these differences in the trends. So so then once we've done that assessment and tried to sort of harmonize the, we're not trying to harmonize, but at least to understand the differences in the trends and to place much improved uncertainties on those trends. Then we will look at the changes in tropospheric ozone with time, accounting for the fact that we actually expect there to be nonlinear trends because of those complex changes in emissions that I showed. We'll look at changes in atmospheric growth rates and stepwise changes, for example, from COVID-19. And we plan to leverage some of the work that's being done by groups represented here in terms of what they've already done with respect to quantifying tropospheric ozone trends. So this is sort of an initial list of the ozone records that we plan to include in the stratospheric ozone working group. So EASI A, B, and C, GOM2, the EASI GOM2 joint product that's sensitive to the surface, the OMI tropospheric column that's a profile retrieval, OMI MLS tropospheric column, the OMI profile from SAO, AIRS and OMI combination that we generate at JPL, TESS and Skiamaki, and then I should have also included CRIS. So we have retrievals of ozone from CRIS at JPL that we will also include. So the secondary goal of the Satellite Ozone Working Group is to sort of coordinate any other TOR-related studies of satellite retrievals of tropospheric ozone. And then we will make the data and model output available in a uniform data format to the community. So our timeline, so right now we're looking at sort of generating this methodology for the direct satellite SON comparisons, and then establishing the evaluation period and a common definition for the vertical extent of the measurements, etc. In winter of 2021, we want to start the analysis with the model output, and then complete that analysis by spring of 2022, and then start writing up results in fall of 2022. So we're holding our first kickoff meeting for the Satellite Ozone Working Group on the 31st of March at 1300 Universal Time. And many of you on this call have already gotten an invitation to that. Just let me know if you haven't and you would like one. So the agenda is to discuss definitions of common tropopause height and the prior, what we want in the file content, so time, lat, lon, the profile, the prior and posterior uncertainty, and the averaging kernel, file formats, and the confirmation of how long the data records are. And that's all I have, so I'm happy to take any questions.
Okay, thank you very much. I see there's one question from Paul.
trying to get to where I can read the. Sorry, can somebody read me the question?
Okay, the first question is, where is the maximum in toast of the west coast of the West Africa coast?
Yeah, I don't know. We think that maximum is real, and I don't know why it's missing from the test product.
It might not be the right trajectories there or something.
Yeah.
No suns anywhere near there.
Yeah.
Well, they're using trajectories to cover the globe, but I don't think that you're getting the advection off the African coast properly. So you don't get the trajectories going there.
Yeah, and upwind there's probably no station.
Okay,
So
Wolfgang.
it looks like Dan has a question related to averaging kernel smoothing.
Yes, it was too long to type, so I hope you can hear me. Yes, you do. So do I understand correctly? So you will consider smoothing issues, but you will, since you mentioned using light files, this implies you are not going to look at time dependencies in the averaging kernel if those are available at all. So is this aspect considered? The possibility that smoothing changes over time.
Yeah, so we will talk about that at the kickoff meeting, but yes, we very much want the averaging kernels, for the specific locations and times, and so that we can assess whether the averaging kernels have changed with time. Because even if there isn't a change in, for example, instrument stability, a change in the distribution of ozone in the troposphere will cause a change in the averaging kernels with time. And so we do want to look at that, yes. And that's one of the things that we would look at with the model simulations.
Okay.
I had a simple technical questions, if I'm allowed to ask it.
Oh dear. Okay. Yes.
Are you planning to read the WODC and NASA Ames SOND files formats? Because you said you want specific formats, but if nobody generates those?
So at JPL, we have a SOND tool that takes in the various SOND data sets, and we use it to compare our ozone products. And so we're hoping that we can, if we get the right data formats, that we can just use that tool.
Okay, because if it's just being able to read them, that should be fixed. Yeah.
Yeah, we can read the SOND formats just fine. Yeah, it's just that we want a consistent data format from all of the providers of the satellite ozone, so that we don't have to, do like a custom comparison for every instrument.
Yeah.
And then there's a question about which SOND products are you planning to use? Certainly the WOUDC, probably the shadows. There's another working group within TOAR-II that is focused solely on the ground-based data. And so they're looking at things like the change in SONDs in 2014. And so we would rely on them to provide us information about whether we should do a correction there, or whether we should exclude certain sites for those years, or how to handle that. So we'll be working closely with that group as well.
Okay, I think we should then move on with the next presentation by Peter Hoare.
Yes, hello.
On OCTAV-UTLS.
Just where's the slide? Okay. Yes, so hello everybody. I'd like to present some, I should say, intermediate results of the OCTAV-UTLS activity, which is as part of Spark working. And OCTAV-UTLS stands for Observed Composition Trends and Variability in UTLS, and involves a lot of people from different platforms, and is guided by Irina and Luis Milan and myself, with a lot of contributions from other groups, in particular using different platforms and types of measurements, which I come to soon. So what's the motivation? The motivation is to focus on the UTLS, and as previous speakers already said, well, there's a lot of variability going on in terms of atmospheric variability, dynamical variability, which to some extent perturbs or makes it difficult to deduce distributions, and in the second stage, trends of species, in particular of ozone, and that's a bit the key motivation. And you all know that looking at trends from different platforms and different combinations of data, if you go further down to 100 hectopascal or even below, where the lowermost stratosphere starts, then you end up in large relative deviations, standard deviations, and variability of trend, but also of composition. And of course, there are several reasons for this. One is that the observations themselves might be limited in terms of coverage, observation geometry, resolution, and uncertainty, but also the dynamics of the atmosphere itself is a challenge in there, and Wolfgang pointed that out. And this is how we want to address this. So we want to develop a unified, consistent, geophysically based framework that can be applied to different observations to account for this variability, and hope to get from this coming a bit more a hand on a consistent, let's say, trend, accounting for the dynamical variability at first sight. And we'll try to do this, or evaluate at least this, based on different platforms and doing it consistently, which means using one consistent way of comparing it to the underlying meteorology and dynamics, which we need to account for to get hand on the trends and also the distributions on the first step. And well, we are still on our way towards a consistent view on this. And just to put a bit more on the motivation in there, here you see something which you might think it's trivial, but I think it's useful to show this one. So what you see here is on the lower panel from ERA 5 at potential temperature level of 345 K, simply the ozone distribution at that isentrope for a given day and step in time. So that's 1st of February to 8. And on top you see the PV distribution on this. And why looking at the PV distribution? Because PV is a dynamical quantity, and it helps you to differentiate between different regimes, in our case, the troposphere and the stratosphere. But you also see that within the stratosphere, and that's the part which is here given in color in both schemes, has strong gradients. And if you again focus on the lower panel, you have the ozone here from the reanalysis. You see that it's first of all strongly undulating here at the location of the subtropical jet. Likewise, the PV, which defines to some extent the tropopause. And on the second set, you see that you have strong gradients of ozone in the stratosphere, which are partly, and that's important, partly mirrored by the PV distribution. For instance, looking here at this kind of perturbation, tropospheric like perturbation, bringing up low ozone values deep into the stratosphere, which are mirrored here in the PV. But it's not always that clear. For instance, looking here over the Northern Pacific, you see that the chemical gradients are much stronger than the dynamical gradients. And that's kind of the challenge which we want to face. But first of all, you see from this immediately that if you do a simple zonal or multi temporal mean, that you average over these kind of undulating subtropical jet location, likewise the PV gradient and therefore the tropopause, and also according to this also the respective ozone variation. And we want to get rid of this by accounting for the dynamics, either in particular looking at the location of the subtropical jet and normalizing to some extent the tracer distribution, the ozone distribution to the location of the subtropical jet by using the jet location itself, for instance, or by using PV, because PV is the quantity which best describes the dynamics in the UTLS which we want to account for. And in the vertical, this looks similar. Just very briefly, a snapshot of potential vorticity at 2 locations, and just think about ozone being embedded in here, and looking at, for instance, an ozone profile here at 60 degrees north. You have a very different distribution here in the lowermost stratosphere compared to just 3 degrees of longitude further to the east. And therefore, yeah, we have to account for these 2 quantities: the location of the jet, so the lateral boundary, as well as the vertical boundary, which is basically the tropopause, of course. And therefore, yeah, we try to evaluate different ways of accounting for this, and there's no really best way. Of course, the dynamics is a key player here, and therefore it makes sense to look at dynamical quantities like the dynamical tropopause, or simply the PV distribution itself, or some higher derived product, which is the equivalent latitude, which is basically just sorting PV in a monotonic way along one isentrope. So equivalent latitude, for those of you who are not so familiar with this, is nothing else than sorting your air parcels by PV. And that this accounts, according to what I've showed here, a bit for the relocation of the embedded tracer according to their PV value. But also we can do different, more traditional metrics. For instance, the jet location defined by the wind maximum, and we can look at an air parcel, how far it is it distant from the location of the jet, how deep is it above the thermal tropopause, or how deep is it above the dynamical tropopause, and so on and so on. And from this simple sketch here, you see already that you might get different results depending on where your air parcel resides, when accounting for these different metrics. And therefore, like I said, it's not quite clear which one is the best one, and which one is the best one given the type of observation you have. And that's kind of the challenge we are still facing at. I should say we wanted to be a bit further than we are at the moment, but we, I think, made some progress in defining some best metrics. And how do we do this? We use the JetPack tool, the Jet and Tropopause analysis tool developed by Gloria Manny and over several years, and Luis Milan, who is part, who is a co-lead. And what it does is simply it provides, based on a set of reanalysis data, a consistent view on the different metrics and the different measures to measure the distances to, for instance, the jet location, like given in here, or the vertical distance to the tropopause, whatever definition you want to see. And the key point is that it is doing this really at the location of the measurements, interpolated in time and space, interpolating reanalysis in time and space, and also providing this on a consistent meteorology. So we decided to use the MERRA-2 reanalysis data set and apply this to all the different data sets, the zones, the LiDAR observations, the satellite observations, and the aircraft observations, to get a really consistent view on this. And one example to illustrate how this works, so you know I'm an aircraft guy, so I start a bit with aircraft, is the Caribbean regular airliner measurements, and they provide a very nice distribution, a large-scale distribution in the UTLS on the basis of regular flights, nearly once a month from basically 1997 on. The data I will show are starting at 2005. They have the high resolution, and they kind of bridge the gap between high precision, high resolution measurements and the large statistics. And therefore I start with this, just showing you some examples how this remapping of coordinates works on this distribution of ozone. And this is shown in here. So in the upper panel, in the upper row, you see simply the data density where the aircraft was flying as a function of, in this case, geometrical altitude, that as vertical coordinate. Here we have potential temperature as vertical coordinate. And all these plots have the normal geometrical latitude as x-axis. And here you see the first way to normalize the data with respect to vertical geometrical altitude relative to the dynamical tropopause. And here we have potential temperature relative to the dynamical tropopause. And as I said, above you see the data density, how it is affecting this, and there is a nice coverage here in the mid latitudes around the tropopause in the UTLS, region for all these data. And here you see the mean ozone, which is a result of this remapping exercise. And while you don't see too much, maybe here the transition from the geometrical means to the tropopause-based means shows already that you get, in some cases, much stronger gradients out. But to decide a bit which one is a good metric and which might be a less well-suited metric, we used the relative standard deviation. And again, you see here that in the key region where you have the strongest gradient, you have, of course, also the strongest variability and the strongest relative standard deviation of the ozone. And you see how the normalization, in this case here, to the dynamical tropopause leads to a further reduction of the variability down here to this plot where we have geometrical latitude and potential temperature relative to the dynamical tropopause, where we have just reduced enhanced variability in here, but a much more reduced variability of ozone, of mean ozone here in the stratosphere. And in this case, one would go, for instance, and maybe prefer these data here to look for trends and do some further analysis, just as an example. And just for completeness, this, of course, was a plot which is based on full annual mean, which does not make really sense, and to some extent, and just to convince you that breaking this down into the different seasons really brings also down furthermore the variability. And in this case, we added not only the vertical distance to the tropopause, but also the horizontal metric, equivalent latitude, as an x-axis to account for the horizontal quasi-isentropic variability of the PV, but on top of this also to vertical measure the distance to the tropopause. And you see that the variability, which is in the annual mean here quite high, is further reduced and yeah, allows for well, hopefully a more concise trend analysis of these data. And of course, we don't want to stick in the aircraft world. We also want to extend and do this exercise in other measurement platforms, for other measurements platforms. And a different example is shown here by work using the LiDAR observations from the Table Mountain Observatory by Thierry Leblanc, who did a similar exercise using the jetpack produced LiDAR profiles which we had, and analyze them in two different ways. First of all, just using a mean geometrical altitude based distance to the tropopause. And what you see here is the normalized standard deviation again of the data set. And you see this large relative variability of ozone, mean ozone around the tropopause, and doing the same now using dynamical tropopause. He used 4.5 PVU as a proxy for the dynamical tropopause, and did the potential temperature difference relative to this dynamical tropopause led to a reduction of the variability, in particular here in the UTLS, at the lowest part where we are interested in, significantly from 50 to 80% to 30 to 60%. I should say in this plot embedded are the data from 2004 to 2018, so it's not a 1 year mean, it's a multi-annual seasonal analysis. And of course, one difficulty also stands out here. It's when you normalize it to the tropopause, you need to somehow account again in upper altitudes that the tropopause is not a source of variability for the distribution in the upper tropopause. Therefore, we have to think about how to separate the stratospheric data a bit from the lower stratospheric data, because a normalization relative to tropopause altitude does not really make sense for a variability which is not generated by the tropopause, but rather by deep stratospheric processes. So we have to think about how to do this transition in here, but that's one of the things we need to address further on. And to show you how this consistency looks into different, applied to different platforms, this is shown here for MLS, ACE FTS, the Caribbean data set, the ozone sounding data in Boulder, and the LiDAR stations. And this is now really done in the same way by applying the jetpack tool and looking for the distribution of the satellite data and also the sparse data. So the satellite data have not been subsampled, it's just simply the climatology as you want. And you see that already based on these very sparse data set, but using the metrics or the way of reprocessing the data already leads to kind of similar data set also for the very sparse data. So if you compare the satellites, they don't look too different. Here you might get something of the sampling issue, but for instance, looking at the sounding data in Boulder, you get a very similar distribution just from this one ozone sounding, and combining different profiles, I think, would help us, or would strongly enhance the reduction of variability and allow for quantitative comparisons of trends once applied to different metrics to these different data sets. And yeah, so that's kind of a first summary where we're at the moment. So we have tropopolar jet-based coordinates, and we could show that they reduce the variability, first of all, of the distributions of species in the UTLS consistently, and that the dynamical tropopause is very important to account for this, and in general, PV-derived coordinates. But also, and this is what I did not show in this talk, but which was one of the results, that the jet location, the subtropical jet location, is also a very useful coordinate to account for this variability down there, independent of the different type of data sets. So these two are key quantities which we want to use to apply them for trends analysis, and that the satellites are not so sensitive to this kind of coordinate transformation. Maybe they have larger averaging kernels, as you all know. But we are approaching trends, but that's kind of preliminary. But I want to show this very briefly. This is an example from MLS using different ways of transforming MLS data into the different coordinates, and it's given here in the different color codes. And Luis Milan, he just played around to look for the sensitivity to this. Did the analysis of the trend in these different coordinates, and then he transformed it back into the geometrical traditional way. So it's a two-term transformation in there. And at that point, I don't want to stick too much here in the trend itself. What I want to point out is here that the reduction of the variability is quite significant, and that's shown here in the lower right panel if we do this exercise, at least with MLS data. And the light colors show you the traditional, let's say, geometrically fixed retrieval level based or pressure and altitude level based trend analysis and the variability of the trend, and doing this in the dynamical coordinates or in some dynamical coordinates accounting for tropopause variability, you get a significant reduction of trends. And similarly, an exercise from the group of Kaylee Walker, also preliminary results, show this in a similar way now for trend estimates, and they looked at the effect of transforming their trends or doing the trend analysis in different coordinate systems, and the effect of the relative standard deviation of the trend. And this is shown in here for different regions. And here in this plot, you see the potential temperature as a vertical coordinate, the relative deviation of the trend. So it's not the trend itself, it's the uncertainty of the trend if you want in percent per decade. And this is done here in color code for different latitude bands. And the key point here is that the solid lines are latitude and the dashed lines are equivalent latitude. And you see, first of all, that the equivalent latitude accounting for the PV, in particular here in the lower stratosphere, in the extratropics, where you would expect the dynamics most strongly affect the trend analysis, significantly reduces the trend uncertainty. You also see what I pointed out a bit earlier, that in the upper troposphere, you have different drivers of variability, and maybe their equivalent latitude is not anymore the best way to reduce the trend. So that's kind of the difficulty we have to face. And also now accounting for to the tropopause further reduce the variability of trends, at least here in the extratropics, if we compare this to the full analysis. And there we are at the moment, and I think we have identified already some metrics or some transformations which have to reduce the variability, and we have already some trend estimates, but I decided not to show them now because we are still working on this, and we have an ISSI fund which we planned to do in the last autumn. For obvious reasons, this was not possible and has had to be postponed until autumn this year or maybe spring next year. And therefore, there we plan to bring all the things together because there are so many things to account for. And I want to stick on or take up the discussion which started off yesterday. My microphone was broken, therefore I couldn't comment my wording. But yesterday, somebody asked for additional reanalysis, quantities, gridding, some thoughts about this. And I made my thoughts up. And I think what's quite easy to provide with all these data is the potential temperature or the PV from a reanalysis data set, at least some tropopause or jet information if possible to apply for this, and also to think about how to link this to some data which have a kernel, because you have to somehow define kind of a mean PV equivalent latitude, whatever you want, or to help people working with the data to filter this. And I think with this we can really account for the diurnal variability to link the tropopause and jet dynamics. Wolfgang Steinfrecht yesterday pointed out that maybe the monthly mean is not the best quantity for all the things you want to see. And if you want to look for shorter term variability, we have to account for the diurnal variability and the dynamics. And that's largely done by the subtropical jet location or the PV. And therefore, these quantities would be great to have them somehow accounted for, at least in a second or a higher derived state of the data, level 3 data or something. And a key are the dynamic coordinates for gridding. Somebody asked this because if you want to account for dynamics, you have to account for dynamic coordinates. But we are not yet through, as I pointed out, looking at the difference between the lowermost stratosphere and the upper stratosphere, or the mid stratosphere, how to best do the transition in there. And yeah, with this, I like to stop here, and I'm open for questions. Thanks a lot.
Okay, thank you very much. But I think we have to move on to the last presentation, unless there's one very burning question.
Sorry.
Okay, I think we should continue with Stacy.
Can you hear me?
Yes, we can hear you.
So good afternoon and good morning for colleagues in the Western US. I was invited to present this collaborative study that was published last summer, which is a comparison of the GTO-ECV and adjusted MERRA-2 total ozone columns. This is largely the work of Melanie and Diego at DLR, and I thank Melanie for providing the slides that are the basis of this talk. So the GTO-ECV total ozone record was presented yesterday, so I'll just summarize it here. It is a GOM type total ozone essential climate variable as a merged record of total ozone from the nadir view instruments of GOM, GOM-2 on METOP A and B, Skiamaki, and ORA-OMI. And as was mentioned yesterday, OMI is used as the reference data set, and the others are adjusted to be consistent based on overlap comparisons with OMI. And it was also mentioned that the TROP-OMI and GOM-2C data will be added in future versions of the data set. So the data start in 1995 and are 1 by 1 degree gridded monthly means. Some validation results were also presented yesterday, and they showed a peak-to-peak amplitude of differences with respect to Dobson and Brewer that varied from 0.5 to 1.5%, and a drift that was well under 1% per decade. So this data set is updated as part of the C3S program, and the more details can be found in the references noted. So the focus of this work was the evaluation of the high spatial resolution of the GTO-ECV data. So we needed a comparison data set with a similarly high resolution. So this is where Gordon LeBeau and I come into this analysis. as a project under the COS-ACVC program, Gordon constructed the adjusted MERRA-2 ozone product, which is a high-resolution data set for model intercomparisons and data intercomparisons and potentially for model input. The NASA GMAO MERRA-2 assimilates profile and total column ozone from the SBUV series of instruments starting in 1980 and continuing until the launch of ORA-MLS in late 2004. At that time, they switched their ozone that is ingested to the ORA-MLS and the ORA-OMI. However, in the assimilated data set, discontinuities can arise when the assimilation from the data source changes, when the data version changes, and during periods of limited or missing data. So the most notable change was the shift from the SBUV to the MLS and OMI, but there are other smaller shifts that occur as well. So to mitigate these discrepancies, which are small, but they're there, we normalize the MERRA-2 in 5 degree zonal means to the SBUV merged ozone data set, which is also in 5 degree monthly zonal means. And this is what we are calling the adjusted MERRA-2. So then we first compare the 5 degree monthly zonal mean time series. The top plot is the percent difference as a function of latitude and time, and the bottom plot is the difference in the standard deviations as reported by each data set. And note that this is not the difference, the standard deviation of the differences, this is the difference of the standard deviations. And the black dashed line denotes the introduction of the OMI data, which is used then in both records after that time period. So prior to late 2004, these data products are completely independent, and afterwards they both ingest OMI data, but those data are processed with different algorithms. The TOMS v8.5 is used in the MERRA-2, and the GODFIT algorithm is used for the GTO-ECV. So in both the mean and standard deviation differences, there's a clear change with the inclusion of the OMI data, most likely due to the significant increase in the data sampling, in one case from SBUV to OMI, and in the other case from GOM to OMI. So going forward, we're going to consider results both before and after the addition of the OMI data. Now, keep in mind that the adjusted MERRA-2 is normalized to SBUV mod. So this top plot is really the difference between the mod and the GTO-ECV. And these results are consistent with the validation results that were reported yesterday, with a slight positive bias in the GTO-ECV relative to mod, which is larger in the Southern Hemisphere. The overall average difference is negative 0.5%. This is MERRA minus the GTO, negative 0.5% in the first period and negative 1% in the second period. But neither of these is statistically significantly different from 0. And then after the addition of the OMI data, we note that the standard deviation of the adjusted MERRA-2 is consistently just a little bit lower than that in the GTO-ECV. So next we look at the drift in the differences. Again, this is MERRA-2, the adjusted MERRA-2 minus the GTO-ECV. 3 time periods are shown. The full time period in black, which is 1995 through 2018. The period 1995 to 2004 is in blue, and the period from 2004 to 2018 is in orange. The shaded regions represent the 2 sigma error on the linear fit parameter, as do the black error bars on the black curve. The 1995 to 2004 drift is noisier, but this is the shortest segment that was fit, so that's to be expected. There is a small shift in the drift from the early to the later periods, but we note that the error bars do not include the instrument uncertainties. So for example, mod has a drift uncertainty that's on the order of 0.5% per decade. So that's going to largely negate any of these differences. and there's no uncertainty on the GTO-ECV either. That the overall negative drift shown in the black curve results from the more negative differences that we saw in the previous plot after the OMI data are added. But with this small inconsistency, the drift is well below 1% per decade. So then we look at the spatial patterns in the differences over the 1995 to 2004 and the 2004 to 2018 time period for each of 4 seasons. The spatial patterns are qualitatively similar for both time periods, and there is a notable longitudinal structure in the tropics in particular, with the adjusted MERRA-2 being more positive in the Pacific and the northern portion of the tropical Atlantic, and more negative in the southern tropical Atlantic. So both the GTO-ECV and the adjusted MERRA-2 show a wave 1 pattern in the tropics in the total ozone, but the amplitude of the wave 1 in the MERRA-2 was smaller, leading to the longitudinal differences that we see in the tropics. So this slide shows a comparison of the ozone anomalies for each data record. The anomalies are defined as the difference from the seasonal climatology computed over the 1995 to 2018 period. And for each grid box, the anomaly time series from each record is correlated. So the map shows the correlation coefficients, and 97.5% of the correlation coefficients are greater than 0.9, and the median correlation is 0.96. So the correlations are highest at high latitudes and in the deep tropics, and this is the regions where the interannual variability is going to be greatest. And then the comparatively lower correlations in the South Atlantic are in a region of low variability, which might contribute to the lower correlations there. And the panel on the left shows the anomaly time series for each record taken from a series of latitudes at the 32.5 degree west longitude bin. There's very good correspondence between the anomaly time series in each of the latitude bands. The lowest correlation occurs in the 10 to 15 south band, as noted before, and that correlation is in the low 0.8. But as noted, this is probably due, at least in part, to reduced variability. But we also note that there is more structure in the GTO-ECV than is seen in the adjusted MERRA-2. And in the paper, there's a further analysis of this, of the interannual variability. And in general, the MERRA-2 showed a slightly lower amplitude interannual variability as compared to the GTO-ECV. So this shows the skewness of the distributions from both of the data records, and the skewness provides a measure of the tails of the anomaly distribution. So cases of significant negative anomalies are in blue, and cases of positive anomalies are in red. Now, both data sets show very similar patterns of the extreme anomalies as identified from the skewness of the distribution. The negative tails of the column ozone distribution are driven by low ozone events in the mid-1990s, when we had a series of very cold Arctic winters that led to greater ozone loss in the Arctic polar vortex. And the high ozone tail is largely due to the weak Antarctic vortex in 2002. And we note that the more extreme events that we're comparing here took place before the introduction of the OMI data into the data sets. So this is not just a case of the OMI data representing the events similarly in both records. So we're also interested in how well both of these high resolution total ozone data records can capture dynamical variability. This plot shows the results of an EOF analysis in the GTO-ECV and the adjusted MERRA-2 in the tropics between 25 south and 25 north. And we find good agreement in the EOF spatial patterns, looking at the first 4 EOFs, as well as in the principal component time series from each of the records. And the first 4 EOFs and principal component time series can be associated with the physical variability in the record. The first component is associated with the QBO, and the plot also shows the QBO 30 index for comparison. The second principal component is largely associated with the solar cycle, as seen, and the solar flux is also shown. The third principal component is a kind of a beat frequency, is the interaction of the QBO and the annual cycle. And the last is highly correlated with the ENSO signal. So a summary of the study, we find very good agreement between the GTO-ECV and the adjusted MERRA-2 ozone columns, with long-term drift of differences well within 1% per decade, and an excellent agreement of the ozone anomalies and also the extremes in the anomalies. And all these results were published in AMT in April 2020, and there's much more analysis that's also included in the paper that couldn't be included here. So now going forward, updates are planned for both products. We noted that the GTO-ECV will have new data sets that are added to it. And we also have a new version of the SPUV merged ozone data set, so we can update the MERRA-2 with the new normalization factors and get that up to date. I think it's not been updated since it was produced going through 2018. So the GTO-ECV, and particularly the gridded component, the high resolution spatial, the high spatial resolution that it provides, is going to be very important going forward. Like Birgit mentioned before, that within the LOTUS studies, we're shifting towards looking towards regional trends, and we're also trying to understand the ground-based data trends. And so particularly for the ground-based comparisons, having the high resolution, I think this was mentioned yesterday, but allows us to kind of translate between what's happening at a station location and what's happening in the monthly mean, so we can do better intercomparisons between ground and satellite data. And I'm particularly interested in the next step for the GTO-ECV, which is the development of a consistent nadir profile time series. So Melanie provided this plot, which is an update for the development of the profile, the merged profile data set. So they're going to be using all of the same nadir view instruments that are used for GTO-ECV, and using the RAL profile algorithm to give you the ozone as a function of altitude. The maps here show the difference between the GTO-ECV and the integrated profile ozone for coming from the nadir profile algorithms for GOME on the left and Skiamaki on the right, and you can see there's quite a bit of difference. So the differences vary by latitude, season, and by instrument. So the plan is to use the GTO-ECV total columns as the reference, and then to adjust the profiles. And to do this, they're going to use a machine learning approach to develop adjustments for the profile that vary with altitude. So it's not just a simple scaling of the profile to make it equal to the total ozone, but it is an altitude dependent scaling. And so once each of the profiles has been scaled accordingly to the GTO-ECV, they can be merged into a consistent record. So this is going to give us an additional data source for the nadir profilers. So when we're looking at trends in the nadir data, we're not just looking at the SPUV products. And with that, I will stop. Thank you.
Okay, Thank you, Stacy. There's one question, Wolfgang.
Yes, Stacy, you showed this lower correlation between the data sets in the South Atlantic region. And my question is, could that just be a noise problem due to worse data due to the South Atlantic anomaly?
That is actually, that's also a possibility, because I know the OMI data is, well, the OMPS data are affected by the South Atlantic anomaly. Actually, I'm not sure if the OMI data are. But yeah, that's also a possibility. And then there's also the, she noted the gaps in the GOM data. So in the early parts of the record, we've got some of the averages from the GTO-ECV have a lesser, lower sampling. And so they're not as representative for the monthly means.
Thanks.
That answer?
Yeah.
Okay, Down has another question.
Yeah, I would like to go back to slide 5. I noted that the drift, the orange line, this is actually the period where you see the largest differences in drift, or the largest drift in the differences between the two data sets, while this is the period where they both use OMI. So wouldn't you expect larger differences in the earlier period?
They both use OMI, but there's also the GOM2 in one and not the other. So the MERRA is strictly OMI at this point, but then assimilated. And the other data set has additional data records within there, which may be accounting for the differences. So the other data sets have been corrected to match OMI in the mean, and I believe one of them also had a time-dependent correction added to it. But there still are additional data sets that go into that. Oh, and Christoph says that the MLS also can impact the total ozone in the assimilation.
Okay.
So, but I haven't looked closely at the time series to be able to answer definitively on that.
Okay.
On what's causing it.
There are no more questions. Thank you very much to all speakers. And we will have a short break now.
And when do we come back?
So I suggest that we reconvene at 6:10 our time.